Okay, welcome to the fourth webinar in our series, Adapting Stormwater Management for a Changing Climate. My name is Franco Montalto from Drexel University. Today, we have two speakers, Art DeGaetano from Cornell University and the Northeast Regional Climate Center, and Eric Rosenberg from Hazen and Sawyer and Columbia University. Before I introduce our two speakers, I'll just, by way of background, mention that this series is sponsored by CC-RUN. CC-RUN is the Consortium for Climate Risks in the Urban Northeast. We are a NOAA-funded RISA with a mission to study the impacts of climate change on the urban Northeast. And you can see the partners in CC-RUN listed here: Columbia, Drexel, UMass Amherst, City College, and Stevens. This webinar series is the precursor to an actual in-person workshop that we will be holding in Washington, D.C. on March 5th and March 6th. The purpose of this workshop will be to discuss with a variety of utility folks, practicing engineers, researchers, some of the implications of what was discussed in the webinar. So our idea for the webinars was to have the opportunity to really explore some of the technical approaches that are being used to incorporate climate change into precipitation time series and IDF curves, but then to synthesize this and sort of discuss the state of the art in the actual in-place workshop. So you see at the bottom of your screen a link. You can go there, you can register for the workshop. If you see the link that says learn more and register the webinars, if you've missed one or all of the previous 3 webinars, you can, once you register, you can actually download these webinars and watch them at your leisure. So just to highlight who spoke previously, so Mark Maimoni gave the first 2. He's of CDM Smith. Dr. Ziwen Yu from University of Florida gave the 3rd, which was last week, and this is the 4th and final webinar entitled Application of a Hybrid Approach to Downscaling and Bias Correcting IDF Curves, with a focus on New York City. Those of you who are professional engineers in New York, New Jersey, Pennsylvania, let us know if you are interested in getting a certificate of completion for your attendance at this webinar. We can issue a certificate that you can use for your continuing education credits. So with that, I will introduce today's speakers. I'll be handing it off to Art DeGaetano, who's a professor at Cornell University in the Department of Earth and Atmospheric Sciences. He's also the director of NOAA's Northeast Regional Climate Center, the NRCC, which is up at Cornell. And Art was also a principal investigator in the Climate Integrated Assessment study for New York. And so we'll hear from Art first, and then Art will hand it off to Eric Rosenberg, who is an associate at Hazen and Sawyer, also an adjunct faculty in the Department of Earth and Environmental Engineering at Columbia, with 20 years of experience in water resources engineering, focusing on a variety of issues from stormwater to climate change. And he's currently managing New York City's Blue Belt system. So Eric will be the second speaker, and then we will open it up for discussion and questions. You have several options. You can use the chat box to submit your questions, and Corinne will read them out to the speakers and we'll discuss them. You can also raise your hand if you'd like to actually speak, and we will unmute you and allow you to ask your question directly. So with that, I will stop sharing and hand it over to Art. Art, are you?
I'm there. Yep.
Okay.
And into slide presenter mode. Go. Couple down. All right. So we'll see how this tag team works. I'd like to start off with a little bit of motivation for the work that I'm going to present, and mainly the work we did was funded by the state of New York, the state of New York DOT, with the same kind of idea or application outcome that I assume many of you might be interested in. Is how can we take what we use in storm design in terms of intensity, duration, frequency curves, and start to get an idea of what they might look like under a changing climate. So of course, in the Northeast, any of the assessments are showing this part of the world, this part of the country as showing one of the largest changes in heavy rainfall. And you can slice and dice or call heavy rainfall by a number of different names, but really, however that comes out, we see this Northeast kind of corridor, the states covered by the NRCC as having showing the biggest change through time. One of the earliest projects that we looked at is we looked at the historical record and really broke it up into two time periods, a kind of an early short time period. We have a 30-year time period there, and also a later time period, and independently did the statistical extreme value fitting to see what would be, how would a 100-year storm compare between these two periods. And in the graphic here inset to the right, if the 2-year, the 50-year, and the 100-year storm were exactly the same in both periods, you would expect those box plots, or the middles of these box plots, to align with the dark black line. But actually what you see is that the box plots are skewed below the line. And the way you would interpret this is what would have been a 100-year storm in the earlier period becomes about a 66-year storm in the later period. Again, keeping in mind we're looking at short periods of records here. And you get a similar relative decrease in the 50-year storm and in the 2-year storm. So in all cases, the recurrence of these big rainfall events is dropping by approximately 2/3. Then our work also went into actually looking to see how can we update these statistics with more recent data. At the time, most places in New York and New England were still operating on NOAA TP40, which had data that was older than I was, over 50 years old. So we did the updates for actually the USDA NRCS. There they do a lot of work with kind of runoff from farms and dams and things like that, where they do the same type of hydrologic modeling. And actually, we kind of like to think this was the thing that precipitated NOAA into updating their Atlas 14 in these regions. And like I said, one of the aspects of our work was not to have these types of analyses be done, every 50 years, but actually have an automated approach. So as new data came in, we could at least monitor how things like the recurrence intervals of different storms are changing across the region. So I'll kind of leave the pretty picture there as the background. So anyway, if we want to look into the future, I assume those of you that have been on the previous webinars have heard about downscaling. So I'll at least kind of, I won't go into the specifics of downscaling, but basically in our work, we kind of looked at 3 spatial scales of data. All of our modeling work was done on the CMIP5 suite of climate models, about 30 different models from different modeling groups. And on average, they're working on the type of resolution you see up here in the upper left, kind of superimposed on the state of Massachusetts. But basically, you have large 1 degree by 1 degree grid boxes. And the dots in this case are the available long-term precipitation record stations in Massachusetts. One way of downscaling is doing this dynamically. So basically using the large-scale global models to feed into a more regional model. So these regional models have a lot more details in terms of coastlines and topography and things like that. But they're still kind of solving the physics of the atmosphere on a smaller scale. So what you see here is kind of a scale that is common to the 2 dynamical approaches where data are available online from the old suite of models, the NARCAP models, and in the newer suite, this is going to be called CORDEX. So this is on the order of about 25 or 30 kilometers on the side in these boxes. And then in the lower left-hand corner, these are also data that have been downscaled from the global models from CMIP-5, but using statistical methods. So here the boxes are quite a bit smaller, as you can see, kind of on the order of 10 to maybe 5 kilometers. So kind of keep those scales in mind as we move forward. So as I said, in our approach for evaluating things, we looked at 3 approaches of downscaling. We looked at the dynamical approaches, and then really 2 statistical approaches. The middle one there, number 2, is pretty much as simplistic as you can get. Basically all we looked at there were precip extremes at the scale of the CMIP-5 models, and then compared how these models simulated precipitation in their historical period and their future period. So we kind of looked at a percent change at that scale. And then in the third method was a different method of statistical downscaling that we developed for this project. It's kind of in a class of downscaling approaches that are called analog methods. And here what we did, or the premise of these methods, is we used basically kind of looked at pattern matching between historical weather maps and those that might have been simulated by the models in the future. So the idea here is not to get down at the actual rainfall amounts, which for various reasons the models might not be that great at simulating, but to be able to see if the models can capture the overall pattern of, say, pressure, moisture transport at larger scales that are conducive to the types of events that produce extreme rainfall in the Northeast. So the first thing, as all good climate scientists, we did a reality check. So how well do these different approaches, these different models do at simulating what have occurred in the past. So basically here what we're doing is comparing the models or the model simulations from historical periods with the actual observations at stations. So in this figure and many of the ones that will follow, just to give you the lay of the land, each of the box plots shown by different colors are the different models in the CMIP-5 suite of global models that we used. The gray bar that always appears on the left is just a simple average of these models. So if we average the daily values from these models together, what we get. And then in terms of the box plots, what we were looking at here in our work for New York is extreme rainfall values at about 50 stations in the state. So basically the box plots here are, we've interpolated the model values to a particular point at a station, and then the bias, the difference between what we see at the station and what the models gave us is given here by the box plots. So something up here in the box plot might be one station, and something down here or down in the outliers might be a different station's results. So if we look collectively at these, it's obvious that each of the models at the large global scale is underestimating the rainfall that's observed at the stations, with very few exceptions. And kind of, you can see there is a lot of model-to-model variability, some doing better than others. But on average, the models are about 75% of what we're expecting at stations. And I guess I should have prefaced this by what we're looking at here is a 1 day, 5-year event at each of these stations. And this isn't all too surprising of a result, because again, the models are looking at rainfall, aggregating rainfall over a large spatial area. So it's not surprising that that would underestimate what's going on at a station. However, I should say that here we also did adjust for that using kind of standard procedures, area reduction factors to kind of go back to the stations, but yet the models are still doing that underestimation. If we kind of change that up and look at the dynamically downscaled values that were available from the CORDEX experiment, here we don't have quite as an extensive set of models. So basically in the CORDEX experiment, we only have 3 model sets to work with. And the idea here is basically what CORDEX does is takes 2 different global scale models, a Canadian model and this EC Earth model, and then feeds them into actually 3 different regional models, a Canadian and a couple of US models, and to look at that. And what we see here, it's the same type of box plots, the 4 model average, the individual models across stations in New York for the 1-day 5-year event. And here the bias has a very different pattern where we have one group of models shown by the red and the green that are overestimating these rainfall events at the stations in New York by about 1.3. And the other set of models basically run by the RCA4 regional model, that's the commonality between the blue and the purple, which are underestimating by about 10%. So again, we're getting much closer to reality by downscaling with these regional models than we did at the original global model scale. Again, keeping in mind our grid spacing our grid resolution is a lot finer as well. And then finally, if we move to our analog approach, the idea here again is we basically have coarse model resolution future dates. So this might be what a weather map is given by the climate model in 2050 in this case. And what we do is we look for very similar days in the historical observed weather maps. So this weather map in 2055 as given by the climate model might look similar to what was observed on this day in 1995 or 1980 or 1955. And from there, a statistical relationship is developed where it's basically, can we kind of have some type of statistical relationship between these historical days, weather maps, so we're looking at arrays of numbers, not just single numbers, and how well are we able to predict this future date. Once this statistical relationship is developed, we can apply it at a finer scale. So we can take these historical days where we do have finer scale data, something more on the order of say 10 or 5 kilometers, and then use this same relationship. The A's and the B's and the C's are all the same. They're just being applied to this higher resolution grid to kind of come out to see what we would see on that future day going on. So we can use this as an example to say, when we have these surrogates of weather maps from the historical period, we can look at what the rainfall is on these days in the historical period at a fine resolution and use that as a surrogate for what we might expect in terms of rainfall in the future. So kind of doing that, and again, the same type of box plots here again, we can apply this to the entire suite of CMIP5 models. And overall, you can see we've really reduced the bias by looking at this analog method, kind of picking days that have similar weather events to those that have caused extreme rainfall and using the rainfall amounts from those analog days as a surrogate for what might happen in the future. What this does have a shortfall, however, in that we can never get more rainfall on any particular day than has happened in the past. So how this affects the extreme series is we might have many more days where we had the highest amount of rainfall. So the wettest day in the historical period, or the 3 or 4 wettest days in the historical period, may appear many times in the future period because those days are the best future analog, but we can never exceed that rainfall amount. If we look across New York State to kind of say, how does that bias using the analog approach kind of map out across the state, you can see not much of a spatial pattern. So really here what we're saying is the pinker type bars show where we're slightly underestimating the historical values by the analog approach, and the lighter blues are a slight overestimation. And maybe if you squint your eyes, you could argue with me that we're perhaps underestimating downstate and slightly overestimating upstate, but all in all, the bias field is pretty smooth across the state. Then we take these relationships, the same relationships, and look at some future periods. So instead of using the model historical periods, we're doing the same type of downscaling approaches, looking at several future periods. We're using a fairly high RCP 8.5 emissions scenario. Again, this is a very short-term future period. Actually, you might argue not future, but to the model it's future, since the model simulations stop in the historical simulations from the model stop in 2005. So what we see in the short term is really not much difference in what any of the downscaling approaches are saying in terms of the percent change in the 1 day 5 and also the 1 day 100-year rainfall amounts, 5-year on the left, 100 years on the right. And say for the most part, these values are increasing by about 5 or 7%. And actually very little spatial variation among the stations. Again, the box plots are showing this change among the different stations in New York. Really the only one that is showing a decrease in this very short period is actually the dynamically downscaled values at some stations, at fewer than 10% of the stations actually. If we do the same thing but move out to kind of mid-century, again, all of the projections from each of the approaches increase. So we see this change in mean precipitation for the 1 day and 1 day 5-year, 1 day 100-year storm going up. You see a bit more separation between the approaches, which with the simple delta method showing about a 15% increase in both the 5 and the 100-year storm. The analog approach that we developed on average showing about a 10% increase, again in both cases, and the dynamically downscaled CORDEX simulations pretty much in between except for the 100-year event where they're a bit higher than the others. I apologize for that. If we kind of move on to the end of the century, we see a very similar pattern where the CMIP5 model, the delta method, increases even further, about a 25% increase in average. The dynamically downscaled showing quite a higher, something around 30% in the 100-year storm. And the analog approach being the lowest of them all at about 15% on average. So this is really, by the end of the century, this is where we might, I don't want to call into question, but at least we have some differences in how this is playing out simply based on downscaling approach. If we look at these values across the state of New York to kind of get how this changes spatially, again, I'm looking at the 1 day 100-year rainfall amounts here. Out at the end of the century, 2070 to 2099. And what I'm showing here, the left-hand columns are the basically the smallest changes that I see across all models and all downscaling approaches. The mean in the middle is the mean of all models and downscaling approaches. And finally, the 90th percentile is the highest. There's only 10% of the model downscaling approach combinations show a bigger change than that. Again, not much spatial variation across the state, particularly in the, and I should mention also at the top, we have the lower RCP 4.5 emissions and higher 8.5 on the bottom. So not much variation across the state. Again, maybe arguing that you see more change in coastal areas than you do upstate. Changes are quite small at the 10th percentile. Almost all things, at least even at the end of the century, seeing some changes that are actually possibly negative, but most being slightly higher than 0% change. At the high end of the spectrum, again, some indication of this maximum or a larger change in coastal areas. And under the high emission scenarios, changes on the order of 60% in the 1-day 100-year storm. So kind of putting that all together, this is where we worked extensively with the state of New York to take these projections and put it into something that they felt was going to be usable in practice across the state. This is the URL to the website if you're interested. What we see in the map is the individual stations that were used in the analyses. Some navigation here in selecting return period, emission scenario, and what future time period you're interested in. And then the main kind of deliverable from the product is this kind of IDF curve and the corresponding chart. So what's shown here in the graph is we're looking at standard IDF curve, so duration across the bottom, intensity, inches per hour along the vertical. And then the two colors here represent the projected range. So you can think of this dark black line as being the projected IDF curve based on high emissions for this mid-century period. We're looking at a 100-year storm in this case. And the pink area representing the range of the model projection. So 80% of the model projections fall within that range. The purple area or blue area and the dotted line represent the IDF curve that is obtained in the current period. So it is based on data. So if I've selected a station, and that is the IDF curve for that station based on that station's observed period of record, along with within the blue band, the 90% confidence interval about that value. It doesn't show up in this screen grab that I have, but basically you can see that observed confidence interval and range either based on our methodology for computing the extremes, or there should also be a checkbox here where you can see those that come out of Atlas 14. So we've incorporated the NOAA values in here to see how the projections compare with what's presented in Atlas 14. And again, kind of what I'm showing here is when we look at either Atlas 14 or this is our analysis that we did for the USDA. It's important to note two things here. You know, the idea of these confidence intervals coming into play in many of the historical products. But then if we look at our IDF curves, you know, the confidence range that you see in the historical projections actually overlap with the model range. So in a lot of cases, what we're seeing in our future projections are not that far out of the upper confidence bands of what we might see historically, and actually a high degree of, or a certain degree of overlap between those two values. And then I think last, before passing it off to Eric, is kind of a different way we looked at this, or actually were asked to look at this for the Port Authority of New York and New Jersey. What they were interested in is if they had a given precipitation amount, say 7 inches, that they knew their infrastructure, pumps or whatever would fail. They wanted to get an idea of what was the probability of exceeding that amount anytime within a 30-year interval. So the graphic we produced for them and as part of our web page is what's being shown here is in the gray area. This is the historical probability of exceeding that 7-inch value at a location. So kind of the dotted line shows that exceeds probability about 62%. In the gray area is the 90% confidence interval around that. And then each of the bars basically equate to, the tops of the bars equate to that dashed line, and the whiskers on those bars equate to the gray area. So really it's not until maybe mid-century, looking at a higher emission scenario, do we expect the do we expect exceeding 7 inches in a 30-year period, or the probability of exceeding 7 inches in a 30-year period, to kind of be significantly above what might have been seen in the historical period. And then by the end of the century, whether we do low emissions or high emissions, those values exceed what might be expected in the base historical period. So I will pass the baton to Eric.
All right, well, thank you very much, Art.
Yeah, and I should, before you jump on, I did just click on the chat. I should mention something that I failed to do. Yes, we're using daily data and using the daily data to go down to the lower durations. Basically, the basis for doing that is twofold. The climate models, at least at the time we did this, were not basically providing simulations at sub-daily resolution. And then we also looked at changes in the empirical adjustments that have been used in the past from daily to hourly, and actually found no change in those adjustments as we looked through time. So we had at least some confidence in the fact that what had been used historically, or at least the relationship that had been used historically to go from daily to sub-daily values, had not shown much of a change.
Great, and that actually leads into part of what I was planning to talk about. Thank you, Art. I'm going to talk about the application of the work that I did. As Franco mentioned, I worked for Hazen and Sawyer, and we developed what are sometimes referred to as forward-looking design standards for the city of New York. But before I get into that, it helps to have a little background on climate adaptation in New York City. Although it's been discussed for a long time in the city, the first official action to start planning for it was initiated by Mayor Bloomberg in 2008. He established something called the New York City Panel on Climate Change, which is sort of the local version of the IPCC. And they issued their first set of climate change projections, downscaled climate change projections for New York City in February 2009. And they published a inventory of at-risk built-in natural infrastructure later that year. So planning efforts were moving along steadily when an event occurred that pushed everything into high gear. And I'm sure you all know that that event was Hurricane Sandy in October of 2012. Resulted in damages of $65 billion, which at the time was second only to Katrina in terms of the costliest weather disasters in United States history. Actually forced FEMA to redraw its 100 and 500-year flood zones along the coastal areas of New York and New Jersey. And as far as stormwater and wastewater infrastructure is concerned, it resulted in $95 million of damage to 10 out of New York City's 14 wastewater treatment plants. That's significant because the wastewater treatment plants are especially vulnerable because they need to be low-lying in order to collect the the wastewater and sometimes stormwater via drainage and then discharge it to the nearest body. So they are a particularly vulnerable infrastructure asset. So at the time, it just so happened that Hazen and Sawyer was already engaged in a study of New York City's wastewater treatment plants to evaluate the potential impacts of sea level rise and come up with adaptation recommendations. And when Sandy hit, DEP expanded the study to include all 14 wastewater treatment plants, and they fast-tracked it over a period of 6 months. So we mobilized the troops and we inventoried over 50,000 assets, and we developed what became the New York City Wastewater Resiliency Plan, which is shown here. The plan concluded that all 14 wastewater treatment plants were at risk in some way, and that 58 of the city's 96 pumping stations were also at risk from sea level rise or storm surge in the future. And the major conclusion of the study was that investing $315 million in adaptation measures could save the city $2.5 billion in emergency response costs over the next 50 years. So why am I telling you all this? Because part of that report also included a study on precipitation extremes and stormwater infrastructure. And before I get into that, I need to provide a little more background on how DEP designs its storm sewers. The foundation for DEP's design standards is something called Technical Paper 25, which was published by the US Weather Bureau, a forerunner to the National Weather Service, in 1955. It's even older than the TP40 that Art mentioned. And that report included intensity, duration, frequency curves, IDF curves, for all the major cities in the country based on rainfall from 1903 to 1951. And the curves for New York City are shown here. They range in return period from 2 years to 100 years. And these were adopted by the city and are still adopted to this day. Here's another view of the 5-year IDF curve. The x-axis is just expanded. The 5-year storm is the return period for which DEP's stormwater system is designed. And the IDF curve shown here is the red line, with the dashed line representing an equation, I equals 125 over T plus 15. This is an empirical approximation to the IDF curve. It was presented in several textbooks in the early to mid 1900s. One of them was written by a Professor Steele from the University of Texas, and so it's sometimes referred to as the Steele equation. And in practice, this is what DEP actually uses to calculate intensity. They calculate the time of concentration for a watershed. They set that equal to the duration of the storm, and then they look at this graph, they don't look at the graph. They use this formula to calculate the intensity. And you'll notice that the equation is a decent approximation to the curve at durations less than an hour, but then it begins to diverge at durations greater than an hour. But that's not generally a problem because most times of concentration in urban watersheds are less than an hour. So this is what DEP has been using for at least the last 30 some years. And the wastewater resiliency study included an analysis of 15-minute rainfall observations from the 4 main rain gauges in the New York City area, Central Park and the 3 airports, over the period 1969 to 2010, and compared that to the original curve from TP25. And you can see here that they were found to be quite similar. So in this particular case, we did not find a significant trend for the 5-year storm. And it bears emphasizing that, you know, these results are very site specific and they can vary even over a few miles from each other, because as Art showed earlier, the general trend for the entire Northeast has definitely been upwards. But for New York City, we couldn't detect a trend in at least the 5-year storm. Okay, so fast forward to 2016. By this time, several climate adaptation projects were underway. East Side Coastal Resiliency, which is an effort to raise a park running alongside the East River in Manhattan's Lower East Side. The South Shore of Staten Island Coastal Risk Management, an Army Corps effort to build a massive wall along Staten Island's shore, which was brutally hit by Sandy. The common theme among all of them is that they're focused on sea level rise, which is understandable given the disaster of Hurricane Sandy, but none of them accounted for the potential changes to precipitation extremes, even those that were accounting for projections to sea level rise, were using historical data to design for their precipitation extremes associated with these projects. And so we embarked on a study with DEP to develop a unified set of design criteria under which changes to the precipitation extremes could be accounted for in DEP's planning efforts. And the first thing we did was to repeat the analysis of a few years earlier, but this time we used data from Atlas 14, which Art discussed earlier. It had been issued for the region that includes New York State since the earlier study was performed. It's a significant step up in not just technology. It gives you the ability to click on anywhere in the United States and get design storm intensities for both partial duration and annual maxima approaches. But it also uses the most updated data. So it's based on data through the present day. And we once again overlaid this on the curves, and you can see, again, very similar, no change. So again, it was really difficult to detect any significant trend. And one nice thing about Atlas 14 is that it also provides this 90% confidence interval. So now we had two studies that failed to show a trend in the 5-year storm. But obviously, as Art mentioned earlier, other analyses definitely have showed trends, even some that Art ended up doing for us that were located just outside the city. And part of our scope was to develop these forward-looking design standards. So we were, when we first started the project, we didn't know exactly how we would do this. And it was really just fortuitous that Art had performed his study on the downscaled climate data. We looked at other methods and other sources of data, but this was really the best source. And incidentally, we later performed our own analysis on downscaled climate data provided by the New York City Panel on Climate Change, and we found the results to be similar to what Art had provided. And here are the results. We set the Atlas 14 data as our baseline and applied the percent changes found by Art for New York City. And you can see the 3 lines representing projections through 2039, 2069, and then 2099. These are RCP 8.5. So this is the most severe emissions scenario. And as I think Art mentioned as well, notice that the first 2 curves fall within this 90% confidence interval. So this suggests that initially in the next 30 to 50 years, broader changes to the distribution of precipitation extremes, if they occur, will probably be difficult to distinguish from natural variability. The other notable part of this graph is what's not shown, and that is the sub-hourly data. And we didn't provide any projections because the shortest duration that Art provided was 1 hour. And Art mentioned that even that 1 hour, those 1 hour projections were based on conventional adjustment factors to daily projections. And that's just because most climate model output is given at a daily time step. And this is a major need for designing stormwater infrastructure for future rainfall, which is the development of projections at sub-hourly timescales, because that's really what drives the design of the storm sewers. So I think it should be an area of research. So here's another summary. As expected, the intensities and ranges of increase with the increasing greenhouse gases in future time periods. And for the highest estimates under the most extreme scenarios, the results indicate increases of upwards of 30% by the end of the century. So once we had the results, the question became how to integrate these design standards in practice. And for DEP, it was important that they maintain the use of the Steele equation. It was an established part of their system. Their drainage plan calculations are all done on spreadsheets, and the equation provides a very simple way of calculating intensity. So what we found in the end was that the 50-year IDF curve from the original US Weather Bureau TP25 could be used as a proxy for the 5-year IDF curve projected for the 2080s. And this was the most convenient method of accounting for the projected increases in intensity. One of the nice things about this type of approach is that it's immediately obvious what these future projections represent in terms of change to risk. So what today has a 1 out of 50, a 2% chance of occurring in any given year, in the future would have a 1 out of 5, 20% chance of occurring in any given year, at least according to the most extreme projections for the 2080s. So then, in another happy coincidence, Mayor de Blasio had just established this Mayor's Office of Resiliency, and one of their first tasks was to develop a citywide set of design standards to account for climate change. And these design standards require all city agencies to at least consider climate change projections in their capital projects. There's nothing binding about these guidelines. They don't need to actually incorporate the standards, but they need to be at least considered in 4 areas, which is temperature extremes, precipitation extremes, sea level rise, and storm surge. And our projections became the basis for the section on precipitation extremes in the guidelines. So another part of our study was looking at recommendations for potentially accounting for increases in precipitation extremes in drainage planning. And there are some general principles that we kind of came up with. I'm sure we weren't the first ones to come up with this, but there are some general principles that can be followed. The first step would be to establish a design standard based on the expected lifespan of a facility. We know that every facility has an expected design life, and once that life is up, there's an opportunity to create a new design for a new standard. So it makes sense to look at the end of the design life of the facility to pick your design standard. Next, we suggest evaluating the hydraulic capacity of the drainage system using the projected rainfall intensities at that time. It's likely that some parts of the system are going to be adequate because they were probably originally oversized. And that's because of standardization. That's because when you design for a, when your calculation tells you you need a 32.5 inch pipe, you round up to 36 inches. So there's probably a little bit of play in the system. But for those where there's not play, you need to explore mitigation options. And the best place to start is in the upstream end. And so they're listed here in terms of increasing complexity. The cheapest, most likely in most situations, is what's referred to as source controls. I'm sure many of you are familiar with this. The most common type of source control is green infrastructure, and these just cut off the runoff at the source. They promote infiltration to reduce the runoff from entering the sewer system in the first place. Alternative conveyance methods such as swales and floodplains can also be explored. And if all else fails, then you start looking to adjusting pipe slopes and pipe sizes. But that obviously can be very costly, not just in terms of construction, but in terms of the effect on the downstream segments. It becomes a domino effect. If you adjust one pipe size, you need to adjust the downstream pipe size, and so on. And so it's really should probably be avoided if at all possible. So right around the same time, DEP was conducting a separate study on how to deal with these projected increases in precipitation extremes. And the study is based on an approach known as cloudburst management. This was pioneered by the city of Copenhagen in response to some flooding in 2011. And the philosophy is that parks and other open spaces can be optimized for their capacity to mitigate flooding during wet weather. They can be designed to serve as detention basins, fed by overland conveyance and street medians and other drainage corridors, and then release that water slowly once the storm passes. So the idea is to sort of manage or accommodate the inundation rather than trying to fight it with storm sewers. And again, it's likely to have cost savings because these are existing facilities in many situations, and when they're not, they probably are cheaper to build on a per unit basis than storm sewers. Here's a couple of renderings that show a median and open space during dry weather and during wet weather. So New York City hired Ramble, which is the company that developed the cloudburst management approach for Copenhagen, to develop a study for New York City with the objectives of reducing the risk associated with flooding, planning for future climate scenarios, enhancing the capacity of the current stormwater system, and providing co-benefits. And they focused on a watershed in Southeast Queens, which is low-lying, a low-lying part of the city. It's known to be a flood-prone area. And although Copenhagen and also Rotterdam have implemented these cloudburst management plans wholesale for their entire cities, New York City was a little more cautious. They wanted to pilot this approach before committing to a wholesale initiative. And the two areas they chose out of Southeast Queens are what's referred to as South Jamaica houses and a neighborhood called St. Albans. So in South Jamaica, the idea is to create a hydraulically connected system of overland detention areas. The runoff would be stored via detention in basketball courts, parking lots, amphitheaters, and then routed through catch basins into subsurface storage before discharging into the public storm sewer system. So you might be seeing by now a common thread among these types of solutions, and that is simply storage. That in many cases is the solution, or at least the most logical solution to these increases in precipitation extremes. And you can see that they come with the co-benefits of enhancing public space, which can help with community acceptance. Here's a rendering during dry weather, and here's a rendering during wet weather. So Hazen is actually doing the design for this. We're nearing the end of the design phase. And the plan is to construct the system, monitor its performance over a period of 5 or more years, at least enough to capture some significant storm events, and then compare the costs of these measures to their benefits in terms of flood reduction. And that's really the crux of the matter. Like most climate change questions, what is the risk we are willing to accept? What level of service do we need to provide? Does it make sense to try to maintain the same level of service, to maintain the 5-year storm design standard, if increasing intensities require upgrading system capacity? Or do the costs outweigh the benefits? And if so, what is the sweet spot we should be designing for? And of course, on top of this, we have the uncertainty of climate change to complicate things. We don't know how these changes are going to play out. We don't know what types of greenhouse gas emissions are going to occur in the future. And particularly for precipitation extremes over, say, something like sea level rise, in many ways, it's a moving target. So we have some big questions to deal with, but in the end, it's a question of risk management, and it's an exciting time to be in the field of urban hydrology and stormwater management. I'd like to thank Art I just wanted to acknowledge Alan Cohn, who was the project manager at DEP for the projects that I discussed just now. And that's the end of my talk.
Thanks so much, Art and Eric. That was great. We have about 6 minutes or so for questions. Corinne, do you want to?
Yeah, so if you have any questions, you can enter them in the Q&A box at the, if you hover over the bottom of your screen, there's a little Q&A button. So you can send questions there, or if you would like to ask your question verbally, you can click the raise your hand button, and then I can unmute you to talk. And for those that were seeking continuing education credits, if you could just type your name and email address into the chat bar, I can follow up with you and send you a certificate.
I'll ask a question on the steel equation, which I've encountered in lots of places. Is that lots of places in New York, that is, not outside of New York, but do you know what the history is of that, or why was it that in the beginning when they started building the drainage system, they didn't have the benefit of decades of data, and so they came up with this equation which turned out to work out, or what is that?
I mean, my understanding is that the curves came first. So the data, they had the data, and they did the frequency analysis on the observations, and they developed the curve, and then they fitted this sort of as an empirical approximation. So that's my understanding, that they developed the equation as sort of a way of simplifying these IDF curves. And actually, if you look at the old textbooks, sometimes they divide the country into like 7 areas. And they, there's a couple of textbooks by Steele. There's one by Venti Chow that shows this. There's 7 areas of the country and different coefficients for each of those areas. So it's a real easy way of just saying, okay, well, you know, right here, let's say A is about 125 and B is about 15. And it kind of reflects the precision, I guess, too, that they were dealing with at that point.
We got some questions online. I want to make sure we get to those. Go ahead, Corinne.
Okay, so from Denise, is the cloudburst planning method being used anywhere else in the U.S.?
Not that I know of. It may very well be. I'm sure Alan would know more about this, but not that I know of.
Alan, if you have anything, if you want to follow up, just I can unmute you if you want to raise your hand, but we'll go on to the next question for now. What is the minimum length of the period that was used by ART to develop future PIDF curves?
Did we lose Art? Art, if you're speaking, you're on mute.
That is exactly what I was doing. We did that in 30-year periods to be consistent with looking at things in comparing the periods. So we didn't want to muddy the waters by using more data, particularly in a period of time when the time series was not stationary at all. So again, that might be a grain of salt in the fact that what we were looking at is changes. So not exactly where I guess where I'm going with that is I wouldn't advocate using 30 years to do this, but using 30 years as your base to look at the change, we felt was the correct approach to do it. Incidentally, in some of the work we've done since, especially at the higher return periods, you actually do yourself a disservice by using a very long period of record when the series isn't stationary, and kind of are finding a sweet spot around 60 or 70 years in doing that.
And Another question, there was a mention by Eric that you could use sub-hourly data to develop the curves. What is the minimum increment that you think you would need?
In New York City, the minimum time of concentration is 6 minutes. So if it's less than that, they round up to 6 minutes. So yeah, most of them are in that ballpark, 6 minutes to 30 minutes or so.
And Alan says New York City is the only U.S. city implementing cloudburst management projects right now, as far as he knows. One more question I see here. Can you explain again about the difference in observed precipitation trends in New York City versus the Northeast region?
Yeah, so I think basically the way I would describe that is not much, particularly when we go into the future period. New York City, I guess I should, let me rephrase that given what Eric said. Maybe Eric will want to chime in. You know, the broader term differences that you see in trend across the region bring in very many stations and smooth for variations in where the rain gauges were and things like that. What Eric's group did was looked at the New York City station in general and would say what he found there, or what they found there, was that New York City itself wasn't quite as, the trend wasn't as strong as seen collectively across the Northeast. Did I butcher that, Eric, or did that?
No, that's exactly right. I mean, I think there's just a lot of station to station variability. Yeah. And as I mentioned, you did some supplementary analysis.
Yeah. And
that showed that. Just
yeah,
that.
and I mean, actually in all of our box plots, those are basically showing the station to station variation across the state of New York. So yeah, that kind of gives you some idea of what's going on there.
Okay, so thanks to our two speakers. Thanks, Art. Thanks, Eric. And with that, we're concluding this webinar series, but we invite you again to go back and listen to any of the other webinars, or re-listen to this one if you want to get more, and join us for the actual workshop. And I guess that's it.
Thank you so much.
Thanks, everybody.
Thanks, Corinna and Franco.
Thank you very much.